So hey everyone, it's me Deepak. So today I'm gonna explain as a demonstration video of this Deevora Axiom, that is the algorithm system thinking platform. Over here you can find various modules that you can explore with. So here for now we just have 10 plus models that consist of the sorting and path finding and graph algorithms that you can visualize over here over the time with the over the size that you can provide or the time or how let's see it. Let's say for example over here in this path finding, let's say for example I'm choosing Dijistra's algorithm, which takes the time complexity as vertex plus edges log vertex. Oh yeah, the sources, let's say this, and the destination is this pink one. Says figure it out. Let's say I'm just increasing the speed in order to see the in order to increase the execution time and also see the results at the very fast pace. So over here, as you can see, the distance algorithm and the distance that is traveled is heading rendered over here, and you can find at the end that what's the shortest path that you can. Okay, over here, this is the shortest path that this detection algorithm found. If I use the heuristic algorithm like say star, so in that case, you can see the it has been faster than the digesters, but the and I get the same optimal path as the digesters. Okay, and also if I use the depth first search over here in this case, it will explore the means it will go depth into the edge height and go, so it will be see here, this is the path that it found over the time. See here, path that is the yellow boxes. And if the same thing happened with the breakfast search over here, so in that case, because it's the breakfast search, it won't be going deep, doing deep dive. It would be looking into the breadthwise that which one is the uh, whether I'm finding the destination that I do require at that particular level. If not, then I'll be after an iteration, I'll be coming back and checking it again. So here that path is this code over here is same path that is length is 34, but faster than the earlier algorithms. So in this you can just compare and play around with these things. And also if you wanted to compare race, you can do the racing stuff. Let's say for example I'm using the sorting algorithm and I'm uh, doing the race between bubble shot and the quick shot. So here as you can see, the bubble shot took a big of n square and the quick shot has big of n log n as its time complexity. And let's say engage this size, you can see based on size, because some algorithms works on the best on the if the size is smaller, some algorithm works best if the size is greater. So you can just play around with it, and let's do this race between bubble shot and quick shot and see who is the winner between these two. So it's obvious that quickshot is the winner, because still bubble shot is figuring out that which element I need to place where and also stuff. Still doing the comparison. Oh yeah, it's still see here. The steps taken is 1758 for bubble shot, and for the same provided elements set of elements 461 steps is required by the quickshot algorithm. So here's the it's clear that the winner is a quick shot, and you can take a screenshot snapshot of it and also share it wherever you do want. See a screenshot shared, and you can simply share it with your who you want to share with it. Great. So this is the racing, and also we just okay. You can do the shorting visualization stuff over here as well. That is, we just provide bubble shot selection shot insertion merge quick for now. Let's say I'm doing the merge shot. Let's say I'm doing the selection shot, and this provided set of elements. I'll just let me just increase the speed, and this is the okay indication that which color denotes what. Let's figure it out. See you. It takes the 461 steps, and it completes in big of n square time with constant space complexity. Great. And if I'll be just going with the merge shot, in that case it would be running see in just 138 steps, because it's the divide and conquer stuff. And okay, as you can see, we can, if you want to play around with, you can go with the race condition race model as well over here. And this was about the shorting and the path finding algorithms, and you can go with the various median spanning tree algorithm as well, cross streams, and also there's topological sort which I have implemented over here. So you can just see the code at the right side, and over here if you want to see in execution that how it's getting implemented, how you can just visualize it over here. So here's chosen the crisscross median spanning tree, and you can see is completed and the total width is this, and they provided details, and you can find the time space complexity for the selected algorithm over here. And you can visualize various data structures such as stack, queue, linked list. Let's say for example I'm choosing the linked list over here. I want to insert 10, and I want to insert 10 20 at its tail. I can just simply do this thing. I can do this 30. I can simply do this thing, and if I want to delete a node, so I can just simply do that as well. uh, I can just reset it. uh, we have queue, we have stacks, a lot of stuff available over here. You can just play around with it, and there's a lot of modification that I want to do with this. It's just I just created it out. I just doing the demo. I'm gonna implement a lot of stuff over in this over the time. So you can see the trees as well. You can insert a value, insert a new node as well over here. Let's say okay, instead of inserting, let's say I do the traverse or something. For the traversing, we does have depth first search, in order, pre-order, post order, and also I can do level order. That is BFS. So let's go with the level order traversal. As you can see, it will go level wise. It will check the root node. Does it has left, it has right. Okay, if it has, then it will explore the left side, the right side, and it is just doing it in it's using a queue data structure. And we does have in order as well, pre-order, post order. Let's see, if I'm just choosing in order, it will go for the left, root, right in this fashion. See, simple. It will go for the 20, 30, 40, 50, 60, 70, 80, like this way. And you can do whatever you want with, you can play around with this stuff over here. You can search as well. Let's say if I want to search node 70, if I will just type 70 over here in this case. Okay, see it found 70 over here. If let's say I write something, let's say 100, what will happen? Because it doesn't exist, it will say buddy, buddy, 100 is not available over here in this tree. And also there's a dynamic programming model also over here. For now I just implemented three problems over here: Fibonacci, zero knapsack, and the longest common subsequence. Let's see, if you wanted to play around with the zero knapsack, you can play around with this, visualize it with the code on the right side as well, as you can see here. And also if you want to play around with this code and see what happens if I change the code in this, so you can do this here as well. See here, this is the actual bubble sort algorithm. Let's say if I remove this step, compare, I'm commenting it out, you can play around with it, and then do the see the visualization accordingly as well. This is the thing that exists in this thing, in this module, algorithm playground. And also there's a compile. You can compile it. Let's say I want to compile this thing. You can see the code at the right side, output at the right side. So this is for now. We have the various question bank preparation. I just implemented some. I just introduced some problems in this. There are a lot of that I won't be putting out in this in the near future as well. So this is about the Deevora Axiom. So hope you find it interesting and helpful. See you.